Good afternoon, everyone. Today's talk is given by Professor Nanditha on the topic Vector and Floating Point Architectures to Accelerate ML Inference on FPGAs. So let me now introduce the speaker, Professor Nanditha Rao. Nanditha Rao is an assistant professor in the VLSI Systems Group at IIIT-Bangalore and an affiliated researcher with the Safari Research Group at ETH Zurich. She is a recipient of the Fulbright Nehru Fellowship of 2023-24. Her research interests are in the field of FPGA accelerators, computer architectures, and processor designs. She completed her PhD from the Department of Electrical Engineering, IIT Bombay in 2017. Prior to that, she worked briefly at Intel on signal integrity, specifically simulations of high-speed differential interfaces. Her current research interests are in the area of computer architecture and FPGA-based systems.
Hello, everybody. Thank you for coming. So I'll talk about this topic today, which is vector and floating point architectures to accelerate ML inference on FPGAs. And I'm not describing the abstract because you've all read it. We'll start with the topic. Okay, so most of you already know machine learning and what is the need for acceleration, background, and so on. So I'll but still briefly go over it. So we all know specifically that matrix multiplication and MAC operations are key to most of the machine learning tasks. For example, specifically, I've taken an example of a CNN, which is used in several applications here. For example, computer vision, NLP, image classification, speech, and so on. And we also know that transformer models these days, architectures are used very widely as well. And for example, if you look at a VGG16 model, for one forward pass, there are about several million, hundreds of millions of MAC operations needed. So that shows how compute intensive the task is. And from the expertise that I have, I'm handling it from the hardware perspective. That is how you can have specialized hardware to accelerate such tasks. So of course, we also know there are several optimization techniques that people try out, such as pruning, quantization, etc. And those can also be handled in hardware. So I'm going to handle this aspect or this problem from a hardware perspective. So to introduce to those of you who are not aware of FPGAs is, so FPGAs are ready-made prototype available boards, which are used in several tasks, such as video processing, image processing. It is used in several aerospace and defense applications, space applications. It is used in high-end computing and so on. And these are boards which you can purchase off the shelf, which have specialized hardware on it. I'll explain that in the next slide. It also has several interfaces which could be interfaced to our computers and so on. And these days, FPGAs also are more complex. They have processors on them, which it could perform and handle several video processing, object detection, live object detection kind of tasks. Okay, so FPGAs are popular in accelerating tasks. And also these FPGAs are also used, if you've heard of servers like on cloud. So these are also available on cloud so that you could access them remotely. So what do you have on FPGAs? So for example, these are the hardware that you can program on the FPGAs. They are available. These are called column-based architectures, which means there are specific blocks such as logic blocks, multiplexers, memories, and so on, which are available on the FPGA for us to program it. Then there are also memories, buffers, and so on, which are available on the FPGAs. You have several other, for example, DSP slices, signal process, which are used specifically for signal processing tasks, which are also available as slices on the FPGA chip, which can be programmed. We have several other high-end interfaces. So for example, it's not shown here, but you have ARM processors on the FPGA chip, which could be used for running applications. There are several serial interfaces. There are PCI Express interfaces, LAN, VGA. So you have all kinds of interfaces on the chip, so on the board, for example. So if this is the chip, you could interface it with several of these interfaces externally. And you have several clocking mechanisms available, which you could use clocks to run at different frequencies and so on. So overall, it is a powerful board, powerful platform to test out your prototypes and also to accelerate certain applications. So just to go in a little more detail, but without going into too much detail also, trying to keep it as abstract as possible. So this is how the chip would look like. It is different from the normal chips that you have on our processors and so on. So what this has is, it has the key advantage of an FPGA fabric, what we call it, is its reprogrammability. So for example, if you have a processor on this mobile phone, you won't be able to reprogram it dynamically. But the advantage of this fabric is that you can buy this FPGA board and then you can reprogram it as many times as possible, as you want, right? And why can you reprogram it? Because there are several of these logic cells here which are capable of reconfigurability. So for example, there are these columns of logic cells, there are these columns of memories, there are columns of IOs. IOs are input outputs. So it could be, for example, an LED, it could be, for example, a switch. So all of these are reprogrammable. What does that mean? So for example, today, if I want to map an ALU, for example, all of us are aware of ALU. It's an arithmetic logic unit. I can program an ALU on this and test out its functionality. And tomorrow, for example, I want to test out a simple multiplier or a divider. I could again reprogram this whole chip to just perform multiplication or division, and I could test out its functionality. Okay, so that is why it is called reprogrammable. And the interfaces on this chip is what makes it reprogrammable. So then you also have several DSP slices, etc. So overall, and even these interconnects, so all of these wires which connect each of these logic blocks and memories, all of them are reprogrammable. So that is what makes this platform very user-friendly, application-friendly, and that is why it is popular these days in many applications. So with this background of FPGAs, I'll now start with the topic. So the topic was collaborative research. Although some of them I have put up are individual projects, I'll briefly talk about each one of them. So the first thing that we did was the first project which we collaborated with Professor Sharat Sinha and IIT Goa was on how can we make a processor capable of executing MAC operations efficiently. Okay, that was a simple topic to start with. So what we tried to do was we picked a processor. These days, RISC-V is a very popular ISA. So RISC-V processor, and we want to handle MAC operations efficiently, more efficiently than existing processors. And we also want to build a memory model which is suitable for such applications. And we want to support variable bit precision. So if you have looked at, or if you are tracking all the ML related research, most of them deal with, for example, variable bit precision, reconfigurable arithmetic, and DSP slices, reconfigurable DSPs, and so on. So what this variable bit precision means is that, so for example, most of the 32-bit processors can only handle 32 bits of data. So if I want to handle 16 bits of data, I still have to go through 32 bits, right? That means that I'm limiting the capability of the 32-bit register. So instead, what I'll do is I'll try to map two 16 bits onto a 32-bit. So that means that the logic should be capable of handling, let's say, 2-bit, 4 bits, 8 bits, 16, 32, and so on. So that is why we call it variable bit precision arithmetic. So all of these were the ideas that we tried to build into this project. So as part of that, we built what we called a vector extension. So vector means that, so in here I'm showing the vector ALU. So we all know about ALUs, that is arithmetic logic units, which is, let's say, assume that there is a single arithmetic logic unit which can perform a single operation, right? Let's say a MAC operation, a multiply and accumulate. So instead, what I'll do, I'll introduce multiple such ALUs in parallel. In fact, in the same ALU, I'll introduce multiple lanes. We call it multiple lanes. So that instead of performing just one ALU operation, I'll be able to perform 8 of them in parallel or 16 of them in parallel. In fact, there is a RISC-V, or most of the processors have an ISA which is called vector extension, vector ISA, which does exactly this. The instructions themselves, when they are executed, they can handle multiple operations in parallel. So this is one of the popular techniques which already exists. So what we did was we took this vector RISC-V ISA and then extended it to make it variable precision. So that means if I'm able to handle 32 bits of MAC operations, I'll make it flexible so that it can handle 2-bit, 2, 4, 6, 8 dynamically at runtime. Okay, so it should figure out that it needs 2-bit precision and handle it on itself during runtime. So this is the original processor, which does not handle the variable bit precision. So this is the regular processor architecture that we know: fetch, decode, execute, and so on. And we extended it to handle this vector processor. And each of these vector elements can handle variable precision. So that was the idea. And we also embedded one more concept here, which is called a bit serial.
Simple question. So this variable bit precision, this idea, is it in order to gain performance or memory?
Both, actually both. So in fact, we see that we are able to speed up the number of CPU cycles as we reduce the bit, go to lower precision. You can speed up the execution because, like I said, a 32-bit register can now hold so many 16-bit values or 2-bit values. And also the memory model can hold now more data. In the same space, it can hold more data. So it was both memory as well as execution speed up.
Is the intuition that you could, in effect, parallelize some of the operations?
Correct.
Is that the root of
Correct. You can parallelize operations. That is the idea of vector anyway. And this vector is now capable of variable bit width, which means it can now perform more operations. So the throughput will be higher. Throughput will be higher. So you see that if you have a lower bit width, then the number of, you can have, this is the speed up actually plotted on the y-axis, is much higher because you're using less number of bits, and now therefore you can now fit it into the same register and also the memory much better. Of course, we should also make sure that if you're going for a lower bit width, your application actually can perform at that lower bit width, lower precision. So there might be some, so lower bit width means also approximation. So if you definitely need a 16-bit precision, you should go for a 16-bit and not reduce it to 2-bit. So if you are going to 2-bit, it means that you are compromising on the precision. So you should also be able to make sure that it doesn't affect your application. So for example, image segmentation may not be really affected much by going from 16 to 8 or 8 to 4. So make sure that such applications don't get affected. So that was the first work. So I'm just going quickly on each of the works so that we don't go into too much technical details also. So the next work that we did on similar lines was, so all of these, this talk is going to be mostly on accelerating matrix multiplications or MAC operations. Okay, so overall, that is the theme. And we are doing this on the FPGA. Okay, so now the next thing we did was, we know we want to do convolutions for CNNs. So how do we speed up convolution? So one of the ways is, of course, you can go by the previous method. You can use a processor, use an extension of the processor, and do all of this that I explained. The other method could also be have a dedicated accelerator. A dedicated accelerator which does not depend on the processor. So previously we said we have a processor and we have an extension here, which is the vector extension. An alternate way is to have a dedicated accelerator with a certain architecture. Now, the architecture we chose was a systolic architecture. I'll come to it in a bit. We also added a novel convolution method, which actually takes less number of matrix multiplications. so that you could again speed up the task. So the whole idea is to speed up the convolution or the operation. Now, the advantage of combining this new method of convolution with the systolic structure we designed is, again, to reduce the time taken or the latency, reduce the number of memory accesses, higher operating frequency, and we also designed this architecture to suit this new method of convolution. And the student involved is also shown. So the way we do it is, in a typical convolution, what you end up doing is you have an image, you have a kernel, and you slide this kernel over the image, one column at a time, and then bring it down one row at a time. And that's how you complete the entire image. And you're doing an element-wise multiplication in that case. In this method, what we did was to do a matrix multiplication instead of an element-wise multiplication. So we do a matrix multiplication of this 3 by 3 with this 3 by 3, and then we store its result. Then slide this over by 3 and not by 1. So if this is a 3 by 3 kernel, you slide it over by 3 columns. If this is a 11 by 11 kernel, slide it over by 11 columns. So you skip so many columns. So therefore, you skip so many multiplications. And you do the same matrix multiplication, and you collect all the results. And finally, what you have to do is you do a diagonal addition of these results that you accumulated, and that will still give you the same convolution result. So you can verify this mathematically also. We found that the mathematically equivalent. It's not approximate, it is exact. Okay, this is just another method we found. And we also found that this architecture, the systolic architecture, I'll just briefly describe what this is. You have several processing elements. So to think of it in a simple manner, you can think of it as a compute element, something that is computing an operation. Okay, so each of this is a compute element, and inputs come in horizontally and vertically. It could perform any operation. In our case, it is performing, let's say, a multiplication or a math. The results will start flowing diagonally. Okay, this is one architecture we chose. And the advantage of this architecture was, I said previously that we are doing a diagonal addition. And here we are actually collecting results diagonally. So both of them go well with each other. So the method that we found goes well with the architecture also. Therefore, it is a win-win situation for both the method and the architecture. So overall, that's the design. And of course, you have several other components around it, like memory and so on. Then what we do is each of this, so this is implemented on an FPGA. And the diagram you see here is an FPGA implemented layout. Now, each of this color you see is one such, in fact, it is one such design. So this systolic array has several other interfaces to it. So you have each of this as one such, we call it a tile. And you can instantiate as many tiles as you have resources on the FPGA. So smaller FPGAs can probably take 15 tiles. Larger FPGAs can probably take 50 tiles and so on. So what you can do with this are, so as you know, each of this convolution can be independent of each other. Right? You don't have to do them sequentially or in serial order. It can be done in parallel because they're all independent. And that's what we do on each of this tile. You do all of those operations in parallel simultaneously and collect the results. So that way what happens is you increase the throughput again. You perform so many convolutions in parallel per second. And some results that we found were we plot the time taken and representative images from certain models here, LeNet, FSR, VGG, and so on. And we tried several designs. I won't go into details of it, but the design 3 that we found was our design here. So this design with this method of convolution and that architecture. We found was having the least latency. So this line here, the purple line, is the design with the least latency. And at least by about 11x, we found that by simply having a different method of convolution, And by mapping it to a suitable architecture, you can reduce the time taken for that entire operation. Okay, and we were able to get some competitive throughput of some several 1.6 giga convolutions per second. Then what we did was the next thing, okay, first we did a processor extension, then we did a specific acceleration. The next thing we tried to do was, so let's say I'm given this particular design. I have mapped it onto an FPGA. Can I map it in a very different manner, in a certain manner, so that I can speed up the execution? Okay, so this is not about some new ISA, new instruction, or a new convolution. It is just about how do I efficiently map it onto the hardware? Okay, are there efficient hardwares on the FPGA which I can map it to? So the questions we ask are, what is the maximum throughput I can extract? So previously I said we got 1.6 giga convolutions. Can I go up to 2 or 2.5 just by mapping it into some efficient hardware? That's the first question. So if yes, what is that most efficient hardware structure I can map to? Okay, so that's what we want to find out. What is the efficient hardware I want to map to? We found a certain structure. I will explain that in the next slide. And of course, we find out what is the throughput for that particular mapping. This was again done in collaboration with Mr. Sharad Sinha. Student was Shubhai. So here I'm showing, so what happens in our FPGAs is that if you have a certain design, so let's say I have this Mac design, I'm going to ask the tool to map it onto hardware. Now, when I ask it to do that, it is going to give me some structure like this. And you can see that this is a very serial structure. Like you have a register connected to another register and so on. It's a very serial structure. Okay. So what we tried to do was we write the code such that it does not map onto this serial structure, but it will map onto some parallel structure. Okay. And that parallel structure that we found, we call it PDAT. What that is it's a pipeline DSP with adder trees. Okay, that structure is already present on the FPGA fabric. It's not something we have created, but it's something that we are mapping our design to. Okay, so instead of letting the tool map it to a serial structure, we are forcing it to map it to something more efficient by writing the code in a certain manner. Okay, and this can be applied to any other logic as well. We tried it for Mac. You could also try it for other applications. Yeah, so in the code, for example, you could, in RTL, we tried this in Verilog. So we are having, let's say, an assignment statement. Now, this assignment statement could be written in a manner in which it can be pipelined, for example. So then you have introduced several registers in between. When you write it instead of a single statement, you write it in multiple statements, break it down. In fact, we can actually ask the tool to do it also, to put in buffers in between and so on. So that way it is going to cut this down into several blocks, pipeline blocks, which can be done in parallel. Correct. So the data flow is modified to put in buffers in between and break up the data path. So this was, again, for each of them, I have just put down the conference if you want to go back and look at it. So we also, this is a method which we follow. That is, once you create this structure, we populate the entire FPGA. That means we use up all the resources on the FPGA, so you get the maximum throughput. So what we found was that a design which was earlier working at a lesser, so this is a table, each of this column shows related work, and the last column is our design. These are resources used, which we don't have to look at. The last row is the throughput. So this particular design that we tried had a lesser throughput. For example, it had 300 to 350 gigaops per second as giga operations per second as the throughput. And by just mapping it onto efficient resources, we were able to get it to 500 plus. And this is on a certain FPGA board. Now, if we actually try to go to a larger FPGA, which has more resources, now, for example, you see that here we have used about 61,000 logic blocks. If we get an FPGA which has several millions of logic blocks, this throughput could go even higher. So the point is that something running at 300 to 350 could be bumped up just by writing a much better data flow model or a code, and by asking it you should also know how to use the tool to map it better, right? So that is one of the works. Yes, one has to be a little bit experienced to find out all the constraints the tool has and so on. Yes, that is true. Yes, so this correct. So we want to automate this task also, so that given any code, we should be able to map it onto efficient hardware. Yeah, that is right. Or the person has to be experienced enough to, so the student had tried this for quite a long time, so that he knew what were the things to be optimized. No. So most of the FPGA fabrics have very similar structures. So this pipeline DSPs, adder trees, etc., are mostly available on all FPGAs. But yes, your question is valid, because what we have tried is only Xilinx FPGAs. So Intel FPGAs, for example, could have a slightly different structure, which we have not tried. But the concept should remain the same, I believe. Okay, so the next thing we tried was, can we change the FPGA's architecture itself, right? So of course, this is not done on real hardware. This is done on a simulator. It's called an open FPGA simulator. This was done in collaboration with a PhD student at Utah and Rapid Silicon. So they have a framework wherein you could explore different architectures of the FPGA. So if you remember, initially I showed there are columns of logic, the columns of memories, columns of DSPs, and so on. So that is the typical FPGA architecture. So the questions that we asked in this problem was, there are several of these DSPs and memories on the FPGA. We call them heterogeneous blocks. So what is the role of these H blocks, or the placement of these blocks? So do they have to be in a column style? Do they have to be adjacent to each other? What is the best way to place them? Can we have a flexible FPGA architecture, which is not conventional? So the conventional was the column-wise structure. Can we have a more flexible one? In fact, this is also a very recent and good research topic, which many people are researching on. People are also working on domain-specific architectures, defining domain-specific architectures for, let's say, ML applications. In fact, if you look at Xilinx or AMD's Versal architecture, they have these vector AI engines. They call them vector AI engines as part of their FPGAs already. Okay, so people have got onto this some time ago also. And we want to explore the location of these H blocks on the layout. So that was the idea. And we used a couple of open source tools. It's called VTR and OpenFPGA. VTR is a tool from University of Toronto, and OpenFPGA has been built by that group that I just showed. So these are the different architectures we explored. So what you see here is a column of memory and column of DSP blocks. So this is how you have typical FPGA structures in most of our FPGAs. This is how you find it. So we try to make it a little more denser. So you can play around with all of these architectures because it is an open source architectural exploration. So we could do all of this. This cannot be done on real hardware because the hardware is already there. So you can't do this with hardware. Then we try to place them, place the DSP and the memory next to each other. We made them dense, we made them clustered, and so on. So what we finally found was that this kind of an architecture where you have clusters of memories. So this is, the yellow is the cluster of memories. This is cluster of DSPs placed quite adjacent to each other. is an architecture which will work out very well for ML applications. Now, what ML applications or benchmarks did we run? We ran what are called CoYOS benchmarks, which are again open sourced, developed at UT Austin. And these benchmarks they have things like matrix multiplication or sparse matrix, SPMV, and so on. So when we did this, we found this architecture was the most suitable for us. And what you see here in this table is these are the benchmarks. So for example, attention layer, convolutional layer, GEM, SPMV, softmax, all of these are benchmarks. So if you go and look for CoYOS, you'll be able to find these. So the tool will actually map these benchmarks onto this kind of architectures. Okay, and we extracted numbers or latencies for all of these layouts that I showed before, and we found that there's about 6% improvement in the latency, what we call critical path, on an average over the conventional. So this is the conventional architecture, and this is our proposed architecture. So over conventional architectures, we have some percent of improvement. Now, this is all simulation. How feasible is it to actually manufacture or generate such kind of an architecture is a different thing, but then at least we show that we don't have to stick to the conventional type of architecture. Yeah. Correct. So in fact, I should have added that slide. So what we would find is that when you map this, so these are logic blocks sitting here. Now, how does this help? So maybe first I'll answer that. How does this help over this? So for example, if the logic, a MAC operation is mapped somewhere in this area, it has a very nearby DSP or a nearby memory to access as compared to this one. Therefore, we reduce the critical path. So that is the answer to why this kind of an architecture is useful. Now to answer how is the mapping problem? The mapping is probably slightly more difficult, and this tool is actually capable of doing that efficient mapping. So it can find out which memory should I use if I map a structure, let's say, to this area. So that the tool is capable of doing. Correct. It is an optimizing that routing. Yeah, most of the challenge here is optimizing in the routing. Yeah, the availability of routes is not an issue. Okay, so we proposed this architecture. Again, we found it was useful. So the next thing we developed upon this was the next work, which we extended the systolic to vector systolic. And the task here is to accelerate, again, the same. First task is the same throughout my presentation. The challenge here is also to make it parameterizable or reconfigurable, which means that the user, this is of course work in progress, but the idea is if I specify, for example, that I need a design with so many vector lanes for so many bits of data, I should be able to get an IP which the user can use. So the user should not have to go and change the code and so on. So it should be available as an IP. And how do you actually partition the kernel and matrices to be able to do this? And finally, we again try some layout level, some mapping level techniques. I will come to that, of how you can efficiently use this. So the architecture, this is familiar. I showed it already. Just that the difference is each of this is now a vector, which means that internally, each of this is going to look like this. It's going to have many more processing elements. The advantage is that I could map in multiple image elements, for example, onto each of these lanes and take in a kernel and reuse it on multiple image components, and the rest of the flow remains the same. Now, the question we asked was, Of course, you can have a single processing element like I showed previously, or you could have multiple processing elements. So finally, when you actually put them on an FPGA, like if I go back to this slide, if you tile it like this, if you create multiple instances, which of these work better? Does this instance, this one work better, a single processing element version work better, or a vector processing element version works better? So that is the question we asked. And yeah, so firstly, we find out what is the role of multiple lanes. So we made multiple lanes, 2, 4, 6, 8, etc. And what we also found was DSPs we know are very efficient on the FPGAs. So they are much faster than the other components, but there are very limited DSP resources on an FPGA, like maybe a few 50s, hundreds of DSPs. But if you look at logic blocks, even if you go back to this slide, there are only few columns of DSPs available. So if you use up all of these DSPs for your Mac operations, I still have so many logic blocks left over. So what we thought, we map some of these elements, components to these DSPs first, use all of them up, and then the remaining tiles could use just the logic blocks. They might be slightly slower, but still we are utilizing all of them in parallel. Okay, so we get some more throughput. So we call this approach as a hybrid tile system-like architecture, wherein you use all of the existing resources on the FPGA. And we also try to find out how many lanes should I have? Should I have like 4 elements in parallel, 6 elements, 8, 10, 12? What is the number that is suitable? Without going into too much technical details, one of the recommendations we had was vector 6 or 8 is the most optimal. The other thing we tried to do was, like I said, do a hybrid approach. And we find that we can actually have more number of tiles. So this is number of tiles versus vector size. The green line is DSP only. This is logic block only, and this is hybrid only. So of course, if you use up all the resources, you can have, like, let's say 70 instances of a design instead of having just 40 instances of the design. And you can also have much better throughput if you do multiple tiles. So overall, the idea was to do a hybrid approach and recommend what is the most suitable vector lane width. So this was one of the more recent works. Then going ahead with a similar topic, we also we had this vector coprocessor from the previous work that I showed, right? We had this vector coprocessor that I first described. So that we tried to integrate with an in-memory compute. This was a work done with Professor Mansoori of IIT Delhi, one of his PhD students and our MTech student. So we tried to do this vector extension as an in-memory compute. Now, what is in-memory compute is that, so most of us know that you have, let's say this is a processor and this is, let's say, memory. Whenever you want to load or store data, you want to go to and fro memory, and the memory is external to the processor. Therefore, it will take so much time, several clock cycles to go and come back, right? And of course, we have caches to handle it, but still, when you have cache misses, you still have to go out to the memory. Now, to minimize that, this is another recent trend. IMC is what is it? It's called in-memory compute. That means you don't have to fetch data from the memory into the processor. You perform computation in the memory. So there are many ways to do it. You can look it up. You can arrange the cells such that it can perform computes, it can perform AND or NOR, etc. Or you could have logic blocks which are sitting close to the memory. It's called near memory compute. So all of these paradigms are very popular these days. So what we tried to do was do this vector computation, in this case vector MAC, in the memory. And of course, it is variable bit precision and so on. It needs some unique data mapping strategy and so on. so that you don't have to bring in the data. And this was an RAM based memory. So that was done at the IIT Delhi side. Okay, couple more works and I'll stop. We did a couple more IMC works. Again, this was in collaboration with IIT Gandhinagar. Yatin was our student. The other two students were from their side. So this was a floating point. So far we have only seen int, right? These were all ints. And we did a couple of works on floats as well. This is a floating point NOR adder tree, NOR gate based adder tree, again, which is based on in-memory compute. And this work demonstrates how you can do floating point max in IMC. Okay, floating point MAC operations using in-memory. So the architecture looked something like this. So this was, if you know the typical SRAM cell, it usually has 6 transistors. This has an additional NOR gate, which is why it is called a NOR tree-based design. And the SRAM cells are built with this kind of a NOR gate tree. And overall, the computation, the idea was to have these exponents, mantissa, sine, etc., mapped onto certain parts of this architecture. And you have an adder tree here, an accumulator, an exponent handling, all of that near memory. It's kind of near memory, actually. And this work actually demonstrated that you can achieve an operating frequency of up to a gigahertz, a computation speed of about 2.6 gigaflops, and a decent accuracy with Linux. The other one is still pretty low, needs to be improved. But overall, this work demonstrates that you can still do floating point max in SRAM with a simple modification to the SRAM cell itself. And another similar work, this was done by Saket, again with the same group at Gandhinagar, IIT Gandhinagar, was to have bit parallel operations. So I said previously we did bit serial operations. So that is, that's not the conventional multiplication. So conventional multiplication involves shift and add and so on. So in bit serial and bit parallel, you slightly do it differently. And they have built some components inside the SRAM array to be able to do that. So this architecture, so for example, it uses, again, in-memory compute to perform approximate floating point computes. The precision is reconfigurable, and it achieved, as compared to other existing work, it did achieve good amount of competitive frequency, and the advantage was it is reconfigurable to any precision. Yeah. So for example, you could use Cadence to test out the designs, or correct, in simulations. So the previous one was actually a layout done. I mean, they could also plan a tape out for this, but right now it is done in simulation. So this work, again, it uses some separators, some normalizing circuits, some extra circuitry added, right? Which can perform this kind of operation in IMC. So this is another work. We are collaborating with Infineon to do very similar floating point IP. We are on NDA and not yet published, so I'm not revealing too much of the work here. But the idea is variable precision floating point unit. Again, we are trying to explore architecturally what architecture suits best to get better latency and throughput for both FPGA and ASIC. Right now, FPGA prototype is in progress. Work is in progress. Yeah, so overall, to summarize, what is the kind of work that we are looking at is reconfigurable processing elements, which could either be normal elements or vector elements, and so on. Overall, the theme was collaborative research, working with different other universities, or one company is Infineon we are working with. How can you accelerate these operations or floating point operations, ints or floats? How do you use SIMD? SIMD is single instruction, multiple data or vector to and in collaboration with a processor, with a processor if required. How do you utilize this? How do you map it onto efficient FPGA resources? How do you accelerate the compute? How do you compute? How do you get better throughput? And another work also that we are working on is high-level synthesis-based methods. So you abstract. So all of this work was done at RTL level, which means you write Verilog, but not many people will be able to write, for example, or want to write RTL level code. So you abstract it out to C or Python, for example, which most people are comfortable with. So high-level synthesis-based methods, again, can be used for FPGA prototyping. So that's again a popular method these days. So those are the things that we are working on right now. Thank you, and also to all the collaborators, plus the funding agencies for funding this work. So that's all I had. Any questions I can take?
Thank you, Professor Nanditha, for the interesting talk. If anyone has questions, it's a time to ask.
Yeah, so this is about the very first one, I think. I just want to get a feel, reconfiguration, and I think it was about changing precision or something like that. And you made a statement that made me ask this question. You said something gave me the feeling that you said it could be done on the fly or something about precision changing. So I'm just curious, is it really possible on the fly, or does it take time? Or I mean, does the mapping have to be redone because you're
Yeah, so reconfigurability is a slightly complex term actually. So when we talk from the perspective of an FPGA, the FPGA is generally reconfigurable, which means that you could change the design multiple times. But then what I mean by reconfigurable logic is that, so for example, let's say you have a certain logic already built. Now this processing element should be able to work at 2-bit or 4-bit or 8-bit, which means, so for example, I could have logic for 2, 4, 8, all of them inbuilt. And at runtime, there could be a controller which detects that, oh, I need 2-bit, and it chooses the 2-bit logic, while the 4-bit logic, 8-bit logic is not being used. So that is one way. The other way is that I have a single logic which can operate on multiple of these elements without the need of a multiplexer, for example, which means that I have a register. Let's say we talk of a register. A register could be split up into 1 32-bit or 2 16-bits or 4 8-bit and so on. So that way, I already have a 32-bit register or 32-bit compute ready. I can use it the way I want at runtime. Right? That means that I'm not reducing the hardware. The hardware is still 32-bit, but I'm using that more efficient. Correct. So we're not reducing the hardware. Yeah, the last method I described is yes on the fly. Typically, otherwise you'll have to redesign the whole thing and reprogram it and synthesize, reprogram it. It will take a few minutes or depends on the design. So if it's a simple design like this, it can take, if the thing is ready, program is ready, it can take a few minutes to reprogram.
Thank you, Nanditha, for the excellent talk and great work, very interesting. I have a slightly non-technical question. In fact, one of the most interesting aspects of your work is the high amount of collaboration.
Oh, yeah.
And since this theme is about collaboration, I wanted to ask you, how did these collaborations come about?
Right.
Because for the benefit of our students,
right.
There are lots of good researchers in India, but one of our weak points is collaboration or lack thereof. I think this particularly deserves a mention, and we would like to ask the secret.
Right. So it's actually started during COVID time when we were looking for people who are working in similar areas and across the country, and also from previous connections and so on. So we got to know about people working in similar areas. Also conferences, right? So we tried to attend a few conferences, go meet people and so on. So that way also a couple of invited talks helped. So when I went, gave a couple of invited talks, people from other universities who were doing similar work, we got together. And especially the Gandhinagar one has been working out very well because we send each year, we send a few people to their group for internships and so on. So that's how it's been working. And they gave us another connect. The Infineon one was slightly more recent. It took a long time to come about. Yeah, but otherwise, most of them have been just through connections who we know.
So very interesting. Lots of different techniques, right? Are there examples where these kind of do they build on each other, or do they add up or multiply up or whatever?
Correct. So this work, especially this one, we worked built upon the previous one. And this mapping strategy could be used for any of those. And this one was built towards the last, the IIT Delhi work. We connected this one there. And this work, we are yet to connect it to other works, but this could be, I think, efficiently used for any other work as well. This one is slightly harder to connect because this involves changing the layout itself. So this is one work which didn't connect with anything else, but otherwise most of them are connected with each other. But what
So I was trying to get a rough feel for when, since you started off the thing, what talking about speeding up ML,
right?
some task. What kind of, if you were to use a bunch of these, what kind of speed ups would you get?
Right. So what we have not been able to do yet is to test it out on an end-to-end application. And for that, I think RTL or Verilog level coding is not good enough. So for that, we need to abstract out a little bit. That's why we're moving towards HLS-based and Python-based. So we would like to apply this to a simple application end-to-end. And I did not bring up another thing because another topic which I think I've discussed with you is because it was not collaborative. That's why I didn't bring it up here. But yeah, we would like to see an application which can be and demonstrate there's a certain speed up. But individually, these have had good speed ups, for example, 11x, 10x kind of speed ups.
What is
Or field programmable gate arrays.
and here most of the work is related to optimization, I think.
This
Can
one
I
of
say?
this work was optimization. This work was optimization. The others are mostly design.
Oh,
Yeah.
nice. In optimization point of view, is it helpful in improving the efficiency in memory management or operational management?
Both. So in FPGAs, we try to do more of operation or compute management because there's only so much control we have on memory, on the on-chip memory. But off-chip memory, yes, that is another thing we are working on as to how to use the off-chip memory efficiently. But that is, I have not presented that work here.
One more question. Here you have defined the ready-made board.
Correct.
That board can be connected to computer directly?
Yes. Yes. So we can directly connect it to our machines and then use a specific tool to program it. So this interface that you see here is where you connect to using a USB to the machine.
Fine. Thank you.
Any other questions? Or do we close the session?
Thank you. Thanks again. Thanks for